Here's a twist on the classic ramp problem. A block sits on a frictionless wedge, but the wedge itself is being pushed across the table, accelerating. With no friction to grip it, how does the block move as the ground beneath it races sideways? Let's find its acceleration in the table frame. Picture a wedge on a table with a block of mason on its smooth sloping face, which rises at an angle we'll call phi, here 45 degrees. An outside observer at rest with the table sees the wedge driven to the right with constant acceleration, capital A. Our target is the block's acceleration in that same table frame. We attack it in two pieces. First, geometry. Because the block must stay on the moving surface, its horizontal and the vertical accelerations are locked together by a constraint. Second, forces. Only gravity and the normal force act, so Newton's second law finishes the job. Start with the geometry. Drop the block's height, y sub b, straight down to the base. The horizontal distance from the block to the lower corner is L minus the quantity x sub b minus x sub w, where L is the fixed wedge length. The slope angle ties them together. Tangent of phi equals y sub b divided by that horizontal distance. Solve for the height. Y sub b equals the horizontal distance times tangent of phi. Now differentiate twice in time. The wedge length is constant, so its second derivative is 0 and phi is a fixed angle. What survives is the acceleration constraint. The block's vertical acceleration, a sub by equals minus the quantity a sub bx minus capital A, all times tangent of phi. The two components are not independent. The ramp welds them together. Now the forces. The block feels only two. Its weight, mg, pulling straight down, and the normal force, capital N, pushing outward, perpendicular to the smooth face. Because the surface tilts at phi, that normal force splits into a horizontal piece, capital N times sine of phi, and a vertical piece, capital N times cosine of phi. Apply Newton's second law component by component. Horizontally, the only push is the normal force's sideways piece, so capital N times sine of phi equals m times a sub bx. Vertically, the normal force's upward piece fights gravity. Capital N times cosine of phi minus mg equals m times a sub by. Two equations and one normal force to eliminate. Eliminate the normal force. From the horizontal equation, capital N equals m times a sub bx divided by sine of phi. Substitute that into the vertical equation and substitute the constraint for a sub by at the same time. On the left, cosine of phi over sine of phi collapses to cotangent of phi, giving m times a sub bx times cotangent of phi minus mg. The right side becomes minus m times the quantity a sub bx minus capital A times tangent of phi. Now gather every a sub bx term on one side. The horizontal acceleration factors out against cotangent of phi plus tangent of phi, and the mass cancels. Solving gives the answer. A sub bx equals g plus capital A times tangent of phi, all divided by cotangent of phi plus tangent of phi. Feed that back into the constraint to get the vertical piece. Recall a sub by equals minus the quantity a sub bx minus capital A times tangent of pi. Drop in the expression we just found for a sub bx. Put terms over the common denominator. Cotangent of phi plus tangent of phi. Inside, the capital A times tangent of phi terms cancel, and the leftover A cotangent term meets tangent to give 1. After the dust settles, a sub by equals capital A minus g times tangent of phi, all over cotangent of phi plus tangent of phi. Both components now depend only on the angle, gravity, and the wedge's acceleration. Now put the wedge at 45 degrees. There, cotangent and tangent both equal 1, so the denominator is simply 2. The horizontal acceleration becomes g plus capital A over 2. The vertical acceleration becomes capital A minus g over 2. Negative when gravity wins, meaning the block still drifts downward. For the magnitude, square both components and add. The numerators are g plus capital A squared and capital A minus g squared. Expand them. The cross terms, plus 2ga and minus 2ga, cancel, leaving 2g squared plus 2a squared over 4. So the magnitude of the block's acceleration is the square root of the quantity g squared plus capital A squared over 2. Two limits make this concrete. Switch off the wedge's acceleration, set capital A to 0. Then the block accelerates at g over the square root of 2, aimed straight down the frictionless slope. That's exactly g times sine of 45 degrees, the textbook result for a fixed ramp. Now push the wedge harder until capital A equals g. The vertical acceleration collapses to 0, and the horizontal acceleration equals g, the very same acceleration as the wedge itself. The block stops sliding and rides along, held in place by the ramp's own push. So by choosing how hard you drive the wedge, you decide whether the block slides down, holds still, or climbs. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.